Well, after that introduction, I think I'll say what my 7-year-old granddaughter would say. Oh my goodness. Uh, I'm honored to be here to give this talk, actually. And it's a chance, it's a little bit different than a normal science talk in that I think it's kind of what I did, like it's a sort of a human thing as well as a purely scientific thing. I started out in astronomy and solar physics when I was very young, around 12 years old. So I've actually seen the whole development of space science. When I had a telescope, when I first had a telescope, there were no satellites, nothing. So I've seen the development of space science. I've seen the development of very sophisticated instrumentation that have been flown on satellites. I see images like this sun, the white light sun, and a picture of the sun taken at a temperature in EUV of several 100,000 degrees, and then a picture of the sun seen at a million degrees. And this is actually a movie, I think. It should be. There it goes. Okay. When I started out, images like this could not be made. That's very interesting. This all worked well. Oh, I know what the problem is. I'm playing with the clicker too much. Let that alone. Leave that laser alone. Don't touch that. Okay, at any rate, images like this couldn't be made. These are made, what we've learned about the sun since I started is an immense amount, especially about the atmosphere of the sun. When I started, the sun was basically a white light object that the astronomers felt was very boring because it's just an average star. The total irradiance of the sun only varies by about 0.1%. Astronomers are used to stars that vary by orders of magnitude in brightness, stars that explode and outshine the whole galaxy. So they weren't very interested in this. But it was then found that because of the sun's magnetic field, it has an atmosphere, which stretches out. That's called the heliosphere, and that's formed with this field of heliophysics. And so as I went along, I got more and more interested in what was going on. And we learned a great deal more, in part because of the development of CCD detectors with very small pixels, and through the development of multi-layer optics. These images could not be made without the ability to coat a mirror with a set of multi-layers such that they would be a little bit like a crystal and would give you a reasonable reflectivity in the extreme ultraviolet. Anyway, let me get on with how things actually were in my career. As I say, I started before satellites. That's me down there in the corner when I had dark hair. And that's me up there when I don't. And I was on a moonwatch team, which was a team that tracked satellites. And it's a bunch of essentially amateur astronomers. And amateur means love, not that they didn't know what they were doing. And we had telescopes set up in the east-west direction. And when the Sputnik, which was the first one launched, I forget was the first or second, would pass overhead, we could see it pass a crossbar, and we would yell "mark," and that gave us a position in the star field, and we had a WWV time signal, so we could record the time. And here's a report on this. I was the first person in Pittsburgh to see an artificial satellite, which was a huge, big deal. This was when the Russians were, this was competing with them. And the newspaper people pulled me out of class. I think I was 15 years old, and they interviewed me. And that night when I saw that, we were understaffed, and I was just lucky to see the satellite. The next night, the roof of the Allegheny Observatory was about ready to collapse with people. But anyway, there's a guy who's lighting a pipe. You could smoke anywhere in those days, and that black thing, the guy's holding the telephone. So, yeah, he's actually calling somebody. It has a wire, it goes into another thing. This is how things were done. There was no orbital debris at all, but you could smoke almost anywhere. Well, my hair got gray, and the situation with the sun changed. And now we're turning the Earth into a planet Saturn. I mean, Saturn's a very beautiful sight through a telescope, and I'm sure when the aliens come, the Earth will look great too. So, okay, to start out with, let's say a few things about the sun for those of you who aren't experts in the sun, and this will orient you. The sun is 8 light minutes away, 93 million miles. It's a big, heavy object, as you know. The diameter is so big that you could fit 100 Earth diameters across it. All you see in this visible light picture are sunspots. Well, those are very important. The sunspots are just cooler areas on the sun. they only look dark because they're maybe 1,000, 2,000 degrees cooler than the surface, which is 9,400 degrees Fahrenheit. This is what the inside of the sun looks like. I think most of you know that in the core of the sun, hydrogen is converted to helium by thermonuclear reactions, and the radiation passes out towards the surface through a radiative zone. The temperature in the core is about 15 million degrees, and as you go out, it's cooling down, and the density is getting less. So as the radiation goes out, the density becomes too small to support and to keep transferring all the energy by radiation. So it's about a third of the way in from the surface, convection starts, or boiling. So the sun starts to boil, and that's called the convection zone. But the gas is still ionized there. So you have charged particles. It's a charged gas. It's a plasma. And as a result of this, a magnetic dynamo is set up. And it's this magnetic dynamo that does all the things. The magnetic field penetrates the surface of the sun and goes off into space. You have a solar prominence, which is like an eruption of cool gas at 10,000 degrees. You have explosion solar flares that go up to 20 million degrees. And then, of course, you have the dreaded coronal mass ejection, which is the thing that really can kill your satellites. You've got like 1 billion tons of matter moving at 1 million miles an hour, or something like that. The surface of the sun is called the photosphere, so that will be and you see those little, I hesitate to touch this thing, but I'm going to do it. These little, you see what happens? That's deadly. That is absolutely deadly. Anyway, the little small things you see there are called granules, and granules are like the boiling. Like if you boil a pot of water on the stove, that's what you would see. And the structures in the sun, you see, when the temperatures are low, they're fine. You see little small things. In the corona, it's more amorphous. You see bigger things. Okay, so to show you how this actually works, this was, again, a white light sun, and this is taken on the same day. We have devices, there we go. We have what's called magnetographs. We can measure the longitudinal magnetic field on the sun through Zeeman splitting spectral lines. And white and black is like north and south polarity, and here's the fields. And the fields arise where the magnetic field is strong, and that's around sunspots. And these areas are called active regions. And then the field lines, we've extrapolated them out into the heliosphere by a potential extrapolation, assuming no forces are really acting on them. And plasma flows along these field lines because basically a charged particle can flow along a field line, but it finds it difficult to flow across a field line. It's like moving through a forest sideways. So as a result of that, when you see the plasma, you see these striations in this total eclipse of the sun, and you see this sort of structure. And this is all delineating the magnetic field of the sun. The magnetic field has an energy density, b squared over 8 pi. And we believe that what happens with this magnetic field, that the magnetic field can sometimes transfer this energy into heating of plasmas, and that's what causes solar flares and mass ejections. Now, when I came here, if I can find When I came here, I was going to work with George Carruthers. In fact, I was going to work on the interstellar medium. But when I passed an office, my branch head didn't expect me, and he was busy, so he decided to dump me, and he dumped me in this office next to a guy that had just got these really great X-ray spectra of the sun. And this was an X-ray spectrum of a solar flare, and the lines here are lines of highly ionized atoms that are only formed when the temperature reaches 10, 15, 20 million degrees. And the guy that got the data was telling me about this, and I was astounded because I thought sun was a boring star, like the astronomers probably thought. And here it had this atmosphere where these big explosions could occur, and somehow the gas could get heated to 20 million degrees and form these various ionization stages. And most of these ions are so highly stripped of their electrons that they're like hydrogen-like or helium-like. They have the same like electronic structure as hydrogen or helium. And in this movie up here, this is the GOES data that you get from NOAA. And every time there's a pulse in X-rays, you see, we can now see where these pulses of X-rays are coming from. But when I started to work, we didn't even know what a flare looked like in X-rays. There was only one rocket thing. Now, how do you study an atmosphere which is really hot? The corona is 1.5 million degrees, and flares are even hotter. Well, this divisible light is what we see. Plasmas that get that hot emit in the X-rays and the ultraviolet. That's where they emit their radiation. So in order to do that, that's why we have space science and go out into space, because these rays don't come through the Earth's atmosphere. So what happens when you're in the plasma and it's hot, you have 3 electrons that collide with atoms and strip them of their electrons. So things get pretty complicated spectroscopically in a hurry. And this is a little arcane stuff, just so you're familiar with it. When I say, you see these oxygen 3, oxygen carbon 6, what does it mean? Oxygen 1 is neutral, and if you take away one of the electrons, it's called O2 spectroscopically. You take 2 electrons, it's O3, and so on. So oxygen has 8 electrons. So actually, there are like 7 different ions of oxygen, all of them emitting in the solar atmosphere. So here, when all the if you have a set of ions of all with the same electronic structure, like 1 or 2 electrons or 6 electrons, that's called an isoelectronic sequence. Okay, so how are these things, how are the spectral lines emitted? Well, here's a high school view of an atom, the electrons going around the nucleus, and all the forces on them, right? So you have positive forces here and negative forces here. And then you have an energy level diagram, because this is quantum mechanics. You solve a Schrodinger equation for this. And you have these discrete states. So one of the 3 electrons can come along and excite an atom in the ground state up to one of these states, and then it just radiates back down by itself and emits a photon. And that's fine. And if we only had 1 ion per atom, the spectrum might be pretty simple. But every time you take away an electron, you change all these states. So now all these ions are emitting discrete frequencies that are all different from each other. It's like having a whole bunch of pianos. They're all not in the same tune. They're all out of tune. And so the number of spectral lines proliferates immensely. So, okay, what determines where a particular ion is formed in the atmosphere? Well, the ions are formed in ionization equilibrium balanced by electron impact ionization. The electrons can not only excite the atom, they can also ionize it and take it up to the next charge state. And when the gas starts to heat up, neutral, say, in this case, carbon, starts to get ionized to carbon-2. And that happens around this temperature in log space. So if you see carbon-2, you know roughly what the temperature is. Now, as the temperature continues to increase, then radiative and dielectronic recombination balance things with the electron impact ionization, and you just go to successively higher ionization states. When you get to carbon-5, there's a big peak because now you're down to the K shell of the ion, and to pull out this, there's only 2 electrons, it's helium-like. And to pull out that one of those electrons, you need substantially more temperature than to pull out the electron from carbon-4. Then you have hydrogen, and finally you strip the oxygen of the carbon of all of its electrons. In the sun and the corona, everything is either carbon-6 or carbon-5. It's almost all stripped. So there aren't many lines for that, but that's kind of nice. Okay, in the 60s and 70s, when I started, many strong spectral lines weren't identified. And there was very little atomic data. That is, these excitations that I'm talking about of electrons are quantum mechanical things you have to calculate. They weren't known. The radiative transition probabilities weren't well known. Very little was known. Suppose you know all these lines, so what and who cares? What do you do with them? Well, it turns out that some of the lines, the ratios of the intensities, can be used to get temperature. They're remote sensing thermometers. Others can be used to get densities. So they're remote sensing sensitive barometers. You can get abundances of elements. And if you want to explain all how the atmosphere works, you have to know what the properties are. So this gives you all the physical properties of what you're looking at. And spectroscopy is the only way to do it. The images I showed in the beginning are pretty, but they don't give you the detail that you get in a really high resolution spectroscopy. Not only that, spectral lines get broadened by the Doppler effect. They have a wavelength, but if the gas is moving away from you, that wavelength will be redshifted, like the expanding universe or whatever. And if it's moving towards you, it'll be blue shifted. And it's also broadened because each atom in the gas will broaden the line due to its temperature. So the spectral line can be broadened by temperature, it can be broadened by turbulence, and it can be shifted due to bulk flows. So we can measure all of that with spectroscopy. At that time, now there's an atomic database called Chianti. Chianti is an acronym which stands for Chianti. the people who developed it were in the Chianti region of Italy when they got the idea to do it. And one of them was an NRL guy, so NRL was involved in this thing too. But now, if you don't know anything about spectroscopy, but you need to know some results for some of the lines that you see in your spectrum, you can go to Chianti and you get some sort of an answer. It may not always be right, but you get an answer. But when I was there was none of that. Okay, to start marching you through what I actually got involved with. Shortly after I got to NRL, I was worked on these X-ray spectra I showed you. And then another guy came to NRL, Louis Feldman, and we started, somebody suggested at NRL that we go to the plasma physics division and start looking at spectra made with laser plasmas. At that time, the fusion program's starting. And the problem is that if you want to go to the high temperature lines, say iron, in the lab before laser fusion programs and tokamaks, there was no one could produce these things in the lab. So spectroscopy kind of stopped with calcium. And up to iron, you couldn't extrapolate wavelengths in calcium all the way up to iron. It was too far. But if you can work in the laboratory with a plasma that can produce these ions, then you can shoot scandium and vanadium and all these elements that are not abundant in the sun. So you can't use solar spectra, but you can use lab spectra. So we started out by going to the fourth floor of NRL, where a lot of rocket spectrometers that were used in early investigations of the atmosphere were stored. You need a small instrument to fit in these plasma machines in a laboratory, at least in those days. Not true now, maybe at NIF. At any rate, we got these things, and we built chambers, and we installed this, and this is a famous laser, I think, at the 100 gigawatt class laser at NRL, a small laser now by now standards. And here's another CO2 laser, and that instrument in there is a spectrometer. And we started to take spectra. We also developed, there were spare parts in the Skylab manned space mission, which NRL had big instruments on. And so we developed the spectroheliograph, which this is a mirror, essentially, that makes an image, but it's also a grating. So the images are displaced by the diffraction of a grating. So we could make spectra and make images of spectra along a film plane. And we did that as well. And so this is some of the details of the laser we used. What makes the laser powerful is it's not so much how much power is in there, but it's how tightly you can focus it. And when your energy is on target, it could only be 3 to 60 joules, but when you put it within 75 microns, you get a huge eruption, and the plasma flies out from the solid targets. So we shot a lot of solid targets, and we got spectra. Here's the titanium-12, which is a sodium isoelectronic sequence. These lines of abundant elements are seen in the sun, but titanium is not, because it's not abundant. It's not an abundant element. And the plasma would blow off like this. And there are density-sensitive lines and temperature-sensitive lines. So we could tell the people that were interested in laser physics, essentially their temperatures and densities. If you tilt the target, it would fly off in another direction. Later, we got data from the Skylab manned space station, and it was like the spectroheliograph I just showed you. So there are images of spectral lines as functions of position along of a film plane. And this one's bright because it's helium, and helium is the second most abundant element in the sun. The sun is 90% hydrogen or so, and 8% helium. All the other elements are trace, they don't exist. So this is a solar flare. When a flare occurs, these elements become bright. And here's a lab plasma to compare wavelengths. So we can compare spectral lines in the sun with spectral lines in the lab, which was very informative about certain properties of the spectrum. Just to sort of cap off this laboratory work, I like hydrogen because the hydrogen wavelengths are like this, and when M becomes large, the lines get closer and closer together. And here's a spectrum of hydrogen itself, taken from Skylab. The Balmer series is a set of lines where N is 2 instead of 1. And here are lines taken in NRL laser plasmas of carbon. So this is carbon-6, and this is fluorine. We have both helium and hydrogen like fluorine here, sets of lines like this. Now, next to these lines, there's something we call satellite lines. These turned out to be extremely important in flares for giving electron temperatures. Okay, so to sort of summarize laboratory results, and these are kind of like, they're not the only results ever gotten of all this work. It's just sort of what I was involved in, what I think was part of a product of what I did with colleagues, of course. We got these high temperature spectral lines of iron, we identified them. in laser-produced plasma. So now we knew where iron 19, iron 20, and iron 21, we knew where the lines were. We knew where forbidden lines of iron were. The splittings between the ground state are close together, energy levels, and they produce lines at much longer wavelengths. And we predicted where they would be, and they've been seen in spacecraft like the Hubble. And of course, there were other people. We had collaborators and competitors here. We especially had competitors in England in doing all this work, and they were very good. And the competition was fierce. We'd put in a paper, and sometimes we get, as we were going to submit our paper, get a paper for them, and on one of our spectral lines we identified they had done 2. So now we had to not send it in, or we had to write a footnote, add in proof that so-and-so had also done this. And we've gotten together recently since all that happened, and now we're all good buddies. But back then we were competing. So the basic impact was that we developed remote sensing tools to determine all these properties, temperatures, densities, and dynamics of high temperature plasmas. Okay, so moving onward, we went to Skylab Manned Space Station, which is here. And the Skylab Manned Space Station had something called the Apollo telescope mount on it. The Apollo telescope mount had several telescopes. NRL had 3 or 4 telescopes. And for 9 months or so, they took data. And people from NRL actually moved down to Houston. And we got some extremely interesting results. We began to understand the structure of the solar atmosphere. So here's above the limb, where you can see lines of neutral lines and lines of highly ionized silicon and sulfur. These lines are all formed at several 100,000 degrees. And they fall off within a few arc seconds of the limb. They crash. They don't go straight in a corona. An arc second is only about 700 kilometers. And from this, we began to understand the structure of the transition region of the sun. And the big takeaway from this is we knew we could measure the densities in here. And we know the volumes because this, you can imagine this is an onion skin wrapped around the sun. And if you take the spectral line intensity is proportional to the square of the density times the volume. So if you were knowing the densities and calculating the volume as an onion skin around the sun, we got intensities that were orders of magnitude bigger than we measured. So what was wrong? Well, not all of this plasma in here was emitting. There was just small little things in here that emit. So the filling factor of this gas was far, far less than 1. So we also got spectra from flares. And the flares gave us electron densities. And for example, this line of O4 and this line are density sensitive. So this is the quiet zone. When a flare occurs, the density goes up and the 2 lines are equal intensity. You know, we can go into why they're density sensitive perhaps after the talk. But at any rate, we were able to measure all sorts of parameters this way. We also, the lines got very broad in some of these transition region events. They were explosive events. So we were beginning to see how the transition region was heated and what happened. These huge chunks of plasma are blown off at a couple 100 kilometers a second. Well, okay, what we knew is from all the spectroscopy is the structures on the sun were tiny. And they were much less than an arc second, even though we couldn't resolve them because the instrument didn't have the resolution. Well, a couple of years ago, Lockheed launched an instrument called IRIS, which is focusing on the transition region with very high resolution, and they imaged them. And these are the things we were looking at with Skylab. So we actually see them, and they look exactly like we thought they would look like, small little things. And you can see that some of them are exploding, and they will produce the broad spectral lines. So this is the slit of the IRIS spectrometer, and this is a slit jaw image. It's essentially an image reflected from the slit. So from Skylab, we learned all about the morphology of the transition region, its temperatures, and how it was structured. And we learned about non-thermal dynamics in the corona too, but the widths of the spectral lines told us about an ubiquitous turbulence that occurs in the corona. And we found out these structures are very small, much less than 700 kilometers. So determining the structure of a transition zone is a major step towards understanding what heats the corona and causes violent events in the solar atmosphere. Okay, well, moving on to Skylab, an opportunity came to launch instruments on a Space Test Program satellite. Basically, somebody at NRL, Don Michaels, convinced the Space Test Program to purchase the backup NASA OSO-7 spacecraft, which had 3-axis stabilized pointing. And we flew Bragg crystal spectrometers on this mission, and also we flew a coronagraph. You could call this coronagraph the father of LASCO, the LASCO coronagraph. And at that time, in the 80s, we had a lot of competition. You know, to get these missions, you're really in combat with your colleagues. So space science is like an intellectual combat. And we managed to get our spectrometers launched and in orbit and get results in '79 before NASA launched their Solar Maxima mission, which was a much bigger mission, had more spectrometers and things. And then the Japanese launched some excellent spectrometers in '81. Spectrometers are two types. They're crystal spectrometers. They can be flat, in which you can have just a proportional counter detector or a Geiger counter, and you rotate the crystal to get different wavelengths. Or you can bend the crystal slightly, and then there's no moving parts, and you get a spectrum which is spread out, and then you need a position-sensitive proportional counter. We got excellent spectra from here, and finally, well, I've had some of my ideas shot down, and this was used, this satellite, P78-1, was used, I guess, in a satellite, an anti-missile, anti-satellite ballistics test. Okay, so why was this important in spectrometry and also in the coronagraphs? The data that I showed you in the beginning was low resolution. It could never compete with our competitors, which at that time was Mullard and the Japanese in flying high resolution instruments. But the instruments that we flew on here were excellent. And so the data we had looked like this is what we worked on. And you see, by now we knew where lots of these lines were, but we couldn't resolve them. That's what we had, and this is what we got on P78. So all of a sudden, we became back in the top competitors instead of second-rate competitors anymore. We had this data as good as anybody else. And we used these data to measure temperatures and flares and get all kinds of interesting results. We could even compare our spectra with tokamak plasmas. This was taken from the Princeton Large Torus tokamak. Now, it turns out some of these lines are formed by a different process than electron impact. They're formed by dielectronic recombination. The ratio of like line J to line W is the temperature. The ratio of Q, however, gives the fraction of iron 24 to iron 25. The temperature ratio here is independent of the ionization balance, but this ratio depends on how much iron 24 you have relative to iron 25. So the temperature of a tokamak looks very much like the temperature of a flare, about 15, 20 million degrees, but there's much more iron 24 in the tokamak than in the flare, and that's because the tokamak is transiently ionizing. So such data is used not only by us in the sun, but also by people doing the laboratory research. Okay, then a new opportunity arose. The Japanese decided to launch a follow-on satellite to their Hinotori, and they called it Solar A. And there was an opportunity to again fly Bragg crystal spectrometers. But they didn't want spectrometers that moved because the spacecraft was pretty light and they didn't want to move it so that it would shake because they had a soft X-ray telescope and they wanted to get high resolution images. So one of my competitors on the P78 called me and another of my competitors, said, why don't you two get together and fly a bent crystal spectrometer? So we did. And there was some fuss and muss about who's going to run this show. But the Japanese did not want involvement with any military organization, not because they were mad at the US or anything, but it was a sort of a pacifist movement. They didn't want to get involved with anything military from anywhere. So basically, Len Culhane at Mullard became the principal investigator, and NRL made a memorandum of understanding with Mullard Space Science Lab that Tim Coffey signed, and Mullard made a memorandum of understanding with the Japanese. So we built components for a spectrometer and sent them to Len, and the instrument was finally finished by Rufferton Appleton Lab and Mullard Space Flight Center, and then it was sent to Japan. And here's the instrument. Here's a kind of rocket that was launched on. This is the biggest door in Japan, in the Uchinura Space Center. And we got a lot of new results with the bent crystal spectrometer because it's getting data all at once. You don't have to scan, so we could get data at a much higher time rate. And here you see a flare that's cooling, where gas is essentially, the lines are normalized to intensity at W, and you can watch the flare cool. And we were able to measure temperature as a function of X-ray class. The X-ray class is what you see when you look at flares and GOES X-ray data. And we found that most flares, thermal flares, never get above about 24, 25 million degrees. And that's due to the magnetic fields on the sun just aren't strong enough to do it. If you look at the stars, the situation is different. This is the product of the density squared times the volume. These are solar flares, and here's some stars. So the stars can get much hotter because they have much bigger magnetic fields. Okay, so what did we get from all of this? First of all, we completely resolved between us and our colleagues the X-ray spectrum of flares. We measured these temperature distributions. The lines, the spectral lines in the X-ray region were all broadened in the beginning. And we know that hard X-ray bursts are emitted during flares. And it was suspected that the hard X-rays penetrate into the chromosphere of the sun and evaporate plasma, actually ablate plasma, which is the correct term, but for some reason, the solar physicists decided to call it evaporation, which it's called to this day. And when it evaporates, it produces a blue shift on the components. And we discovered that with the P78 instruments and measured it. However, we also modeled it with 1D hydrodynamic models. The models didn't reproduce what we saw, which was one of the reasons we flew with Bragg spectrometers on Yoko. And it was only relatively recently that we, I think, sort of reconciled the models with the Yoko data and have shown that, in fact, this chromospheric evaporation works. And it's my colleague there, Dr. Warren, who was the first to actually do that with Yoko data, although it was simulated by a Japanese graduate student. At any rate, we did all this sort of stuff. We measured the electron densities and spatial ratios. All this was flares, and we also measured element abundances in flares. So this was a major step towards understanding what causes them, because we began to measure their properties. But most of the properties we measured were global. So the question of what happens when you look at flares in detail, and to do that, we went to the next stage, which was the NOTI spacecraft, Solar B. So Solar B was a much bigger spacecraft than Solar A, and involves instruments from Lockheed, this white light corona, and the Japanese. The Japanese built a big mirror, 50 centimeter mirror, and the focal plane package, which has all the goodies on it, was made by Lockheed. The Center for Astrophysics made a grazing incidence high-resolution X-ray telescope, better than the one on Yoko. And then we were involved, we had the same collaboration that we had with Mullard. Len Culhane remained the PI. The University of Birmingham got involved. Goddard Space Flight Center was also involved with us as a contractor, subcontractor. And we built a 3-meter-long high-resolution spectrometer that we call it the extreme ultraviolet imaging spectrometer, because we could now image in spectral lines. This was a major achievement because, look, when you take a picture with just a multi-layer, each pixel is just a picture of whatever coating that multi-layer has. But if you want a spectrum of that pixel, you have to take that light and then disperse it into a spectrum, which is going to lower the intensity, right? Because you're going to spread this light over all the wavelengths. So this is one of the first instruments to do this for the corona, although it was done before. These things are like, they take years to build and do, and people get totally involved with them. In the course of all my work with the Japanese, 3 major Japanese scientists died of various causes. You get so involved, you become attached to them, and the current PI of the ice spectrometer, the original one is retired, is a woman who just recently got married. And I went to the wedding in England, and she said, go in and look at the wedding cake. I said, why? So I went in and I said, well, I don't see a wedding cake. And she said, well, what do you think that is? And so that's the wedding cake. So it's X-ray telescope and ice are the chocolate batter, and this is a white batter, and these are little chocolate things around the solar panel. And there they are up there, and there's a model of a spacecraft. So you get very attached to these things. So the NOTI spacecraft, these are the principal people. Len was the first person involved, and Louise was the second. And there are 3 PIs of this instrument. There's one in England, which was either Len, and now it's Louise. And there was me in the United States. What happened is NASA made an agreement with the British to supply parts for the spectrometer. Then they issued an announcement of opportunity to propose to do that. So we had to compete. And we won the competition in part because we'd done so well with Yoko. And so we got to supply parts to NASA. NASA supplied parts to the British, and NASA had the ITAR agreement, so we didn't have to worry about that. So now, in Japan, the Japanese always have a PI, and the PI was Tetsuya Watanabe, and Hirohara was the person put in charge of actually doing the work there for a lot of it. Now, here's how ice works. The sun comes in and goes through a filter which rejects white light. And we have multi-layer coated optics of molybdenum and silicon, and an articulated primary mirror, that is, it moves. And half of the mirror is coated with one wave band, so we get one wavelength band, and the other with another set of coatings gives another wavelength band. The light gets focused on a slit, goes through the slit, hits a grating with the same multi-layers, and then 2 CCDs. So we built our components and sent it here to the British. The British, I think in Rutherford, assembled the whole instrument, and it got shipped to Japan. Here's a picture to give you some idea. It's a really big instrument. This is Clarence Corndike and NRL, keeping it from being contaminated. I'm proud to say that our instrument has very little contamination. It will take years for contaminants to really lower its sensitivity. Here it is mounted on the spacecraft, and so anyway, there it is. Now, what do we see? Well, it's a spectrometer. So you get a slit, and you have spectral lines. And here are some of the lines we saw of highly ionized iron and silicon. Our spectra is so deep and they're so high resolution that about 40% of the lines are new. About 40% of the lines are still unidentified. Now, just having a spectrum is what's been done in the past. The thing you want to know is where in the flare structure are you looking, or where in the sun are you looking? So this is an imaging spectrograph. So what we can do is we have a slit that can scan an active region of the sun where you have sunspots. And here, there's a spectrum. Now, we don't throw away the spectrum, but if we integrate over the spectrum and lay them side by side, we get an image. So at each of these points where this slit is, we know the temperature, the density, the motions, and the non-thermal velocities. And we know where in the active region, what kind of structures we're actually seeing. Okay, so what do we see? I think I probably have to click on this. Okay, what we see here is an image of an active region taken in different spectral lines. So we can scan, and this is what happens. So as you're going up to higher ionization stages, you're seeing higher temperatures. So here we're at about 1 million degrees. We were at several 100,000. And now we're going up to 1.5 million. And over here, we're looking at the Doppler shifts of the lines. This is a different active region, but it doesn't matter. And you're looking at the non-thermal motions. As we get to the very highest temperatures, which is, I think, iron 15 or 16 on this graph, you'll see that the active region becomes much more amorphous. The structures are bigger and more diffuse, and all the high temperatures concentrated over here. So this is the first time in the corona that we're able to make such detailed images, so that we can relate this sort of thing to theories of heating of the solar corona. Another thing we discovered, here is an image of the active region in iron 12 at 1.6 million degrees. When you make a Doppler image, that is, you look at the spectral wavelength of iron 12 and make an image of that, and you say that blue is coming towards you and red is going away from you, you see that in the core of the active region where it's pretty bright, the Doppler images are small, they're like white. There's a few red patches. But when you get out in the edges here, you see this big outflow. And these outflows, the plasma is flowing outward between about 60 to 100 kilometers a second. And it's been predicted by some people that this was predicted at the edges of active regions, and it would contribute, may be a major contributor to the solar wind. So my paper was evidently refereed by one of those people. So, I was very happy. I just needed to add some references, some citations, and it got published. But this is one of the, I think, important discoveries from ice. It's still not known for sure whether this actually reaches out into the solar wind, or whether these are just long field lines that bend over somewhere. We can't see. It's very hard to model the magnetic field of the sun accurately in the corona. We're still not doing that. Well, anyway, I haven't said much about what's happening here. What are the fundamental processes? One process that is believed to heat active regions is called nanoflares. And what happens in the nanoflares are the foot points of these magnetic field lines are moving around. And they twist. And when they intersect each other, they cause what's called a magnetic reconnection phenomena, where the field readjusts to new structures and you get heat released. We are now, it's been for a number of years, this process has been modeled, and we've got a rather sophisticated model at NRL, constructed by Russ Dahlberg, where he's doing just that. We have this like tube, this box, and he's moving around the foot points, and just by resistive dissipation, heat is being released. So he can send us the temperatures and densities and velocities of all this gas in the cells. And what we've done is to take our spectral lines from ice and feed them in there and say, what intensities would we get from these structures? And what we get is pretty much what we see in the sun. We're able to model the structures we see in the sun, and this is kind of what it looks like. In particular, there's this differential emission measure, which is the square of the density times the volume. Here's a simulation, and here's the ice data. And here's Harry, because he's the expert on generating these differential emission measures from the data. So we're actually able to test coronal heating models this way. We actually found that the nanoflare model, well, it may or may not work too well. It's not clear. Another model was that plasma is ejected from the chromosphere into the corona, and that's what heats it. We're not agreeing very well with that model either. But we're able to do these for the first time. Now for flares, it's also similar. With flares, we have a big eruption, and what's believed to happen in a flare is that right here above flare loops is a process called magnetic reconnection. And here, what happens is the field lines form and they split, and some of them come back down and are closed this way, while others propagate outward and form a coronal mass ejection. So this shows what actually happens when a flare occurs. So you have loop structures like this. The mass ejection occurs here and creates plasma jets that go up and down. Heat goes down to the chromosphere and evaporates gas into the flux tube, which makes the X-rays that you see. And when the flare occurs, these things occur in multiple loops. They look like slinkies on the sun. And you get these big outbursts. So we're able to test theories of chromospheric evaporation. We can see the plasma coming up there now very well with our data, and we're modeling all this and learning a great deal about it. The plasma that goes out forms a coronal mass ejection, but that's somebody else's process, not mine. At the top of the flare loops, we use our spectral line intensities to generate emission measures and temperatures. And at the tops of flare loops, frequently we get an isothermal plasma. All these points cross at about the same point, at about 14 million degrees. So basically, we're learning a great deal about plasmas. We've learned about the temperature distribution, the densities, the mass motions, and all the stuff I talked about, and maybe new sources of solar wind. We've also found some large abundance anomalies I don't have time to talk about. But basically what we're now starting to do is understand the fundamental physics of the atmosphere. We're able to model these processes with MHD and other models and actually compare with our data. And our data are now providing tests for these things. So for the first time, we may be actually understanding what we see in the sun in terms of a physical model. Okay, the final thing I want to mention briefly is the future. What do we want to do next? Well, we wanted to build a huge instrument called Solar C, a package of 3 instruments that would essentially model and image the sun all the way from the photosphere to the corona with the same spatial resolution. Well, we studied this for 10 years and we came up with beautiful proposals. Unfortunately, the cost about $1 billion. And times are tough now. This was a collaboration between NASA, JAXA in Japan, and the European Space Agency. And none of the partners could get together and agree on anything. So the Japanese last year submitted a big proposal, which we helped them develop, to their JAXA. And JAXA looked around and said, where are your partners? And well, they're somewhere. And so they said, no, we can't fund this because we don't have any guarantee that the partners are going to agree with us. The Europeans tried it on their end, and they proposed this thing called EPIC. But because the Japanese wouldn't say for sure whether they were going to do it, the Europeans couldn't say they were going to do it, and NASA kind of kept quiet during this whole thing. So this is something for the future, but if we built Solar C, then we would have the ultimate spectrometer to view temperatures and densities all the way from the corona where you have big structures through the transition region where you have tiny things down to the photosphere. What I'd like to do is go into this reconnection region, which is very dark. You don't see anything from it. It's hard to believe that it's actually producing anything. But the predictions of MHD modeling of reconnection are that you get magnetic islands. And in the magnetic islands, particles can be Fermi accelerated, and that's what causes hard X-ray emission and flares, which goes up into hundreds of kilovolts, and it goes to the chromosphere. This will produce polarization because the excitation is all along a beam. And I could measure that with Bragg crystal spectrometers very well. We did it at Lawrence Livermore with an EBIT and published papers. So I would like to make a new Bragg spectrometer experiment where you have the crystals with the planes of diffraction like that. Then I would have a polarizer. And I would like to look at the beginnings of flares with helium and hydrogen like iron and see if we actually see this polarization. Well, these are some of the colleagues that I didn't do all this alone at NRL that have helped me out and outside of NRL. And I'd especially like to thank my wife and the rest of my family. My wife didn't divorce me, she didn't kill me. So obviously we have a good relationship yet, so that's fine. And in summary, X-ray and EUV spectroscopy are the key to really measuring things and understanding what's happening in the sun. So we can, with imaging spectrometer, we've entered a new age where we can use a spectrometer and see where the spectral stuff is coming from. And I feel extremely privileged to be a part of this exciting adventure, and I want to thank you all for listening. I think I've gone a little bit too long, but thank you.